Welcome to our video on TensorFlow with C++, where we introduce the TensorFlow C++ API. The main reason you use the C++ API is when you require efficient inference for your models, as is the case when you want to serve them in a production setting. Also, it'll be helpful for us to have some familiarity with the C++ API when we go over TensorFlow serving in the next video. First, we'll go over the general setup you'll need in order to use the C++ API. Next, we'll go over the general usage and look and feel of the API, and we'll finish up with the most common use case for the C++ API, loading and performing inference with exported saved models. Getting set up to use the C++ API is nearly identical to the process of installing TensorFlow from sources, and I'll link the instructions for that in the additional resources slide. Until recently, you required the full source code of the TensorFlow repository in order to access the C++ API. As of very recently, there are some clever things you can do with Bazel in order to include the TensorFlow source code in your projects without actually having direct copies of the TensorFlow source code there. I'm going to provide that in the repository that we have on GitHub for the course, but we're not going to go over the details of how that's done in this video. I do encourage you to read the workspace file that is going to be in our GitHub repository so that you can see how I was able to access this API without having it cloned directly inside of our project. But for the video, we're going to go with the standard approach, cloning the GitHub repository, and using include statements in our C++ code in order to get access to the source files. So we're also going to need Bazel. If you don't already have that downloaded, you can install that now. There's a link to the installation instructions in the additional resources slide, so you can jump over there, install it, and come back. And on that note, I should mention that TensorFlow does not currently support building TensorFlow on Windows with Bazel, but for any brave users out there, there are links in the installing from sources page for building the TensorFlow with CMake, which may work for Windows users, but personally I wouldn't recommend using TensorFlow on a Windows machine, period, in the first place, if you can help it. Working in a Linux or Mac environment is going to be much easier all around. Once you've installed Bazel, I'd also recommend that you go and skim through the installing from sources page, also linked in the additional resources slide, since that's going to go into more detail on some external dependencies when you're building from sources, depending on whether you're using Mac OS or Ubuntu. They're pretty basic dependencies such as NumPy, so I'm going to assume from here on out that you've installed them. And then after that, you can open a terminal, cd into the cloned repository, and run /configure. That's going to configure your environment. Again, this is just the same steps you would do for installing from source. The configure script is going to ask you a series of mostly yes or no questions, and the pass of things like your Python distribution. You're free to answer these as you please. They're essentially just personal preference. And your answers to these questions aren't going to affect how we use TensorFlow in today's video, but you are required to answer all of them, since otherwise TensorFlow won't be able to build. So again, this is the simplest set of steps in order to use the C++ API, and these are the set of steps recommended on the TensorFlow website. Luckily for us, you're going to be having direct access to the code in our GitHub repository, and that's the code that we'll be looking at today, which gives you access to the TensorFlow source code directly without having to have copies of the source code directly in your project folder. So now we're going to transition over to our editor, where we're going to look through a first example snippet of how to use the C++ API. So we're first going to go over the code snippet itself, and then I'll walk you through how the skeleton of the project needs to be in order to have this code actually run successfully. The code that we're going to be looking at first is actually a snippet example directly from the TensorFlow website, the C++ API main page. And I've actually added a lot of comments to that example snippet to make it a little bit more clear where things are coming from and how things are happening. So we're going to pretend the comments aren't there in today's video, but I definitely encourage you to pause the video in parts where you may be confused and read the snippets, or of course directly read the source code from our GitHub repository. So we only include three things. It's going to be a client session file, comments, the standard ops file, which is going to give us the TensorFlow ops namespace, and of course tensor.h, which is going to provide us with the TensorFlow tensor object. And right here, so TensorFlow in the example snippet online, you'll see actually uses using namespace TensorFlow and using namespace TensorFlow ops. That doesn't really tell you where these objects are coming from, so instead I've replaced those to using namespace declarations with individual ones that show you exactly the objects that we use in this example snippet. We're going to be using TensorFlow scope, output, tensor, client session, as well as the const and matmul operations. It should be no surprise that client session is going to replace what we usually call the tf.session in our Python code. Things like TensorFlow scope are roughly analogous to tf.variable scope as seen in the Python API. And of course, TensorFlow tensor is going to represent our familiar tensor objects. and TensorFlow ops contains the various operations. In this case, it's a little bit different. We have, for example, matmul, which in the Python API is, of course, a simple function. Here, and with all operations actually in the C++ API, they are classes, but the way we interact with them, as we'll see in just a few seconds, is to make it seem as if they're functions. It's a little bit odd, but these are conventions that you get used to after working with the API for a little bit. So we're going to enter a simple main function, a wall of comments from me that you are free to read, and the comments are all talking about the creation of the root scope. The root scope is going to give us a handle to the scope that's going to be passed to all operations we create thereafter. So in the C++ API, anytime you create an operation, and operations are these things like const and matmul, you have to, as you'll notice right now, pass the root scope object. You can imagine it similar to the Python API if we had to pass our tf.variable scope object to every single constructor that we use to create an operation. So C++ API should be no surprise, of course, it is quite more verbose than the Python API. You have to do a little bit more work yourself, but hey, that's what we expect when we work with one of these lower level languages. So above each of these three calls that gives us a tensor or operation, we have a simpler pseudocode that shows us what's actually going on. We're going to create A, which is a matrix, a constant matrix that has shape 2 by 2. Its entries in the top row are 3 and 2. Bottom row are -1 and 0. We'll be making heavy use of the curly brace initializer list approach to creating objects in C++. So these things are going to be converted into the correct objects, the correct matrix and tensor objects by the constructor of const. But as with most objects in the C++ API, we can get away with the simple curly brace list-like approach. Similarly, we create a vector instead of a matrix this time called B. It has just 2 entries, 3 and 5, made in the exact same way. And to illustrate how to do an operation like matrix multiplication, we use the matmul constructor. And this is what I was talking about when I said that instead of treating it as if it is a class object, which it is, matmul is a constructor. TensorFlow recommends that we do this functional-like style where we do auto v, and v is going to contain the result of what we would type in Python as tf matmul a and transpose b. In order to write that in C++, we have to write the bit more verbose version of passing it root. And this is an illustration of how, in addition to passing root, in addition to being able to just pass the root object by itself, we can also pass with opname. This is how you name your operations in the TensorFlow C++ API. So this operation will get the name v. We pass the 2 arguments, a and b, and we specify that we want b to be transposed. Very similar to actually the tf.matmul function in the Python API. And this is a common thing in the C++ API. When you have an operation and you want to pass in some options, you use these static things like transpose b on the matmul class. And to see the list of possible options that you can pass to each operation, you go to its respective documentation on the C++ API section of TensorFlow website. Okay, so to recap, we've created A and B. We've created an operation that multiplies A by B transpose. And now we have to do one more thing. That is, of course, run this graph. We've made a very small graph, which, by the way, to be clear, is not something that you typically do in the C++ API. We'll be going over the more common use case of what you do with the C++ API, and that's just simply loading models and using them. But when you're actually graph building and making your own graphs from scratch inside the C++ API, which is a bit more work than you would otherwise have in Python, these are the main ideas and conventions and patterns, if you will, that you'll be using. Having some scope object, using these class constructors as if they are functions in order to get your operations and tensors, and so on and so forth. But something that you'll use in both this example and also the examples when we load our models and use them is running in sessions. So to do this, you have to first create a vector of tensors, which will have our outputs. As of now, it's empty, but session run call is going to fill those outputs with the result of our computations. So we have to create a client session object, associate it with the root scope of our graph, and then very similar to the actual Python API, we just call session.run. This is what we usually call our fetches argument, which is simply v, the operation of A times B transpose. And we pass the address of our outputs vector, so that the session can fill that with the result of the computation. We wrap it with tf-check OK, which will terminate the program if anything goes wrong, and show us the error message that resulted from whatever problematic session run call we just issued. Lastly, as a quick check to see what we got, we access the result, which is just the first entry of our outputs vector. There is only one because we only wanted to issue one operation. And now we access the matrix method of any tensor object. This kind of syntax derives from the C++ eigen library that TensorFlow uses for storing the tensor data. And all we need to know is that to actually access the results of a tensor, the data that got returned by the session run call, we call matrix. We pass the expected type of the output. The type of our output is going to be the same as the ones that we use to compute the mapmul operation, floats. And the matrix method will output something that can be used with output streams. So we can use the log info and actually print it to our standard out. So again, I don't want to dwell too much on this example, which again, you are free to browse on the C++ main page of the documentation for TensorFlow. But we're going to now move on to what the more common use case that is, oddly enough, not too documented on the website, and that is loading and using your saved models with the C++ API. So what we're about to see is a quick file I made myself, and it's going to load the model that we used in the previous sections and send it some simple inputs so that we can get the results of its predict calls. And again, after we walk over the source code, I'll show you how we have access to these different header files here. But for now, just note that we're loading some header files called loader.h, tag constants, session options. I'll point out individually which one of these we're using as we go through the code. Also, we're going to need access to the path of our export directory. So by the time you see this code, it's actually going to have command line arguments that you're going to pass to give the export directory. In order to not have too much clutter inside of this code snippet for the actual video itself, I'm going with the cruder approach of actually including the string path to my repository for this course. Not a recommended practice, but only for the purposes of this video and not having too much clutter in our code. Again, up front, I'm going to show the main using declarations so that we know what types we're going to access in the code below. Even better would be me not including these at all and actually using the full qualified name anytime I use an object from TensorFlow. But again, we want our code for the video snippets to be nice and compact, and so I'm doing it this way, and happy compromise between the full name qualifications and the even less explicit way of saying using namespace as TensorFlow does on their website. Okay, so the process for loading a saved model is pretty straightforward, and you're going to be doing it the same way for any use case you have. First, you're going to make a saved model bundle object. For anyone wondering, I am wrapping this with a shared pointer object instead of just directly having the object access, because passing around copies of pointers is going to be less computationally expensive than passing around full copies of our object, and TensorFlow recommends operating under value semantics as opposed to move semantics. And so to comply with that, I generally prefer to be working with pointers when passing my data. And this save model bundle object is going to contain, as the comment indicates above, our session and metagraph def, aka everything we need to both load and run feed dict inputs through our model and retrieve them as output. In order to load the model, I have to specify where its contents are on the file system. For me, I'm placing those in section 5/export dir. Export dir is the same directory that you specify in our Python when we call the estimator's export save model method. And it's technically actually one directory beneath that directory because TensorFlow makes those timestamp directories. So export dir is actually one of those timestamp directories. In your code, I'd recommend that you have some way of checking or of grabbing the newest timestamp directory out of that, something that TensorFlow serving will do automatically for you. Again, for the purposes of this short snippet, we just have it directly here as the contents of export dir, just to make sure we're on the same page, is assets, variables, and the save model file. I misspelled save model. Now that we have our path, we just need to we create our session options and run options objects. We're not actually going to use these. You're free to use them to configure and customize your session and run. Session options is going to be the same kind of object that we used to use by TensorFlow config protos. And the run options is the session run calls argument. It's also an argument in the C++ API as well as an argument for session run in the Python API. Again, I don't need to customize anything here. I'm happy with the defaults, so I'm just creating them because they are required that we pass them on to our load save model. So this is the big workhorse for us. This is the one that's going to load our model from file and also create our TensorFlow session. It requires we pass the session options, the run options, the path to that export directory, the associated model tags. So I'm using TensorFlow save model tag serve. this is actually just set to a string that is called serve. The reasons for choosing serve aren't particularly interesting other than it's the default signature. It's the default tag used for loading your save models. Again, just conforming to these conventions that the C++ API has. And finally, I pass in my save model bundle. Since I'm using a shared pointer, I have to say .get in order to actually provide access to the underlying raw pointer, because gasp, TensorFlow is expecting a raw pointer here, not a smart pointer like shared pointer. But that's not up to us, so we pass them what they want. Again, so after this point, as long as I've gotten an OK status returned and the program hasn't exploded on me, all the information I need, my metagraph def and TensorFlow session, are stored in my bundle object. So now I'm ready to start performing computations with it. As a simple test sequence of words, I'm going to pass in a true statement. I like dogs, they are cool, I do believe that. And so now I need some way of converting this sequence of words into a tensor, and so that is the next snippet of code. I first get the number of words that are inside of my sequence by calling words.size and casting that into an int. Words.size returns a size t object. Don't want to get any warnings by my compiler. I then instantiate a words tensor, which will soon contain the I like dogs, they are cool sequence. I specify that it needs to have type string. So this is analogous to, in Python we had dtype equals tf.string. In TensorFlow you have dtstring. And similarly, in order to specify what we usually say as shape equals 1 num words, I'm saying tensor shape 1, which is the batch size of 1. I'm only using one sequence. My batch size is 1. And it's going to have num words. Here comes the part that's a little bit odd. In order to actually fill our words tensor with the contents of our I like dogs, they are cool sequence, we have to, first we grab a mutable handle to the underlying data container of the words tensor, and a flattened out handle. As you can see by the comment, welcome to C++, things are a little bit less simple than in Python, but this is the way you do it. So now we have access to tensor data, which if we fill tensor data with any content, it's going to be the content of words tensor. So we need some way of copying our data into tensor data. It's pretty simple for us because we already technically have a flat sequence. Its shape is 1 by num words. We don't have a full batch, so we don't really have to flatten out anything our own. But in order to do that, we just call the C++ built-in copy n. And this is just a standard way of copying one sequence into another sequence. It can be read as start at my source container sequence, which is words, start at its beginning, copy over num words elements, aka all of our elements, into tensor data, which is the flattened out version. So for example, if we actually had more than one sequence, if our batch size was 5, for example, we'd have to first manually flatten out our words vector, so that we could make this call, or we could iteratively copy, but the point is that you have to actually copy it in flattened out like this, for better or worse, probably worse, but anyway. Okay, so now we've specified the tensor we want to feed in, we put the data inside of it. Now what do we do? How do we actually get this thing to run through our model? Well, this thing is going to be part we typically call of the feed dict inside of a session run call in Python, so now we need to build that the C++ version. So that's going to be this feed inputs object. It's going to be a very, very simple mapping from string to tensor. X, if you'll recall, is what our predict mode of our TensorFlow estimator expects for at prediction time. So this is saying find the tensor inside of your computation graph inside the model that we've loaded called X, and we want to set that to words tensor, just as you'd interpret the feed dict in the Python API. We have to do the double curly braces instead of single because unlike the Python API, which is flexible and session run can take things like strings up to arrays or dictionaries, we have to be a little bit more particular and consistent in the C++ API. The C++ API expects that the feed dict can contain one or more pairs of strings and tensors, a vector of them. We're only going to do one. We only want to pass in X as our feed dict, and so we're done from there. A side note is that actually this is going to be converted into a TensorFlow feed type. That's one pretty neat thing about the C++ API of TensorFlow. You got to give hats off to them. Instead of having to instantiate their custom types like feed type, and there's also TensorFlow output, TensorFlow input, they can be implicitly converted from more common, more familiar objects like vectors and pairs. so that we don't actually have to figure out, okay, how do I handle the constructor for this new type, this new type, this new type. But anyway, moving on. As usual, we need to create the container that we're going to use for our outputs. It's going to eventually get filled with them. It's empty for now. As well as our fetches, which is, be no surprise, is the same as the session fetches argument that we used in the Python, but this is the C++ version. And what I want to get from our graph, given the words tensor that we fed in, the I like dog sequence, I want to get its prediction, which I've somewhat poorly named Pred's words. I think that was a carryover from an earlier section we had where that name actually made sense. But just know that this is a tensor in our computation graph that gives us the predicted category in string format, word format, words, Pred's words. Alright, and here's the climax of the program, our call to bundle session. Remember, our bundle is a shared pointer, and so we access its session attribute, and then we call the session run method. We give it our feed inputs, the fetches that we want to get, an empty initializer list, which stands for feed outputs, something that we're not really concerned with, but we have to pass it because this is C++, and that's the signature for a base session object. The client session object used in the previous example is a little bit more flexible. It has a few more signatures for session run, but turns out that the TensorFlow save model bundle object that we're using, its session is just a base session and has less signatures for run, so we have to pick the one that works the best with what we got. Again, pass in the address to our output sequence so that can get filled, and we get the status returned. So this time, instead of doing what I've been doing with tf check OK, which seems to be the TensorFlow idiomatic way of handling exceptions, let's say I don't want my program to explode if a session run call goes wrong, and I want to gracefully handle that and have my program continue running, or in this case, return an error status. But anyway, the main way you interact with these status objects is you check, is my status okay? If not, show me the error message. And then you can pass that on to whatever error handling thing that you like to use. Okay, so I've run my sequence of words through my graph. I'm all good. How do I actually see and use those results? Similar to what we saw in the example snippet earlier, since my output is just the single category, I'm actually going to use the .vec instead of .matrix because I'm one dimension lower. I just want, in terms of the object I'm trying to access, and it is a single string, a single predicted category. And so I do the eigenlike syntax, and I call vec standard string, and now I have my greatly named Pred's words object. I can check its num elements method in order to see the total number of entries inside of it. For us, it's going to be 1. And the way I access those elements, the most common way, at least that I've seen, is I iterate over the total number of elements. So for I equals 0, I less than outputs num elements. And then I use the main way of accessing one of these eigenobjects, which is the parenthesis operator. They don't have a bracket get item operator like we see in, for example, Python arrays or anything like that, or even vectors as here. Instead, you use the parentheses operator in order to get the ith entry of our Pred's word. Usually what I like to do is when I have more complex graphs than this, I'll actually just dump the outputs tensors and their crazy eigenobjects into just simple vectors of strings for further processing downstream. So quickly, let's see what this looks like, at least on a computer, if you're running this and things don't go wrong. Got a quick screencast here for everybody. So I'm inside of our AI with TensorFlow directory in a terminal, and I want to run this program that we just saw. So with Bazel, you do that using Bazel run. I also pass -c opt, which is means use the optimal configuration. Use those things like those fancy compiler instructions. So I call run. This went deceivingly fast, but because I had already built it earlier, secret. But it shows you the common things you see as info statements when you're using save models. So, but because I had already running save model bundle, it'll then say running the legacy init op on save model bundle. That's the same as the init op that we pass in our Python code. And then it says save model load for tag serve, status success, yay, nothing went wrong. Tells us how long it took to load the model. And here are the two info statements at the end of the program that we saw. Pred's words has 1 elements, and it said that the category of my I like dog sequence is talk, religion, miscellaneous. Sure, I can agree with that. So that either means that the 20 newsgroup dataset that this was trained on had a lot of people that were very religiously enthusiastic about dogs, or this is something that it's not used to seeing, and this is its best guess. I'll let you decide. Back to the code, let's see how I set this up. So remember, this is a Bazel program, and when you're working with Bazel, you need build files. So in the same directory as section 5, you will find a file called uppercase build, and its contents are very short. Remove some distractions here. So in order to build the TensorFlow, in order to build the example.cc file, now note that this is actually something that you will see on the main C++ API page of TensorFlow, because this is the example snippet that it was taken from. Instead of using cc binary, which is the built-in Bazel version, we use a fancied up version from TensorFlow called tfcc binary, which we load from the TensorFlow Bazel file. A little bit more on that in just a moment. And we pass the normal arguments that we pass a cc binary rule. If you're not familiar with Bazel, this is going to look pretty strange. You can look through the various tutorials on the Bazel website, which will walk you through exactly what these mean. Briefly speaking, I'm defining that the rule I want in order to make this is example. So that's something that I'm creating and defining myself. I'm saying that this file it has source files, example.cc, that's the one that actually defines this file, the implementation of it. And the external dependencies, aka the header files I included inside of that, correspond with this list of Bazel rules. Now, in the TensorFlow C++ API documentation page, you see that it looks like you just have this portion here. The reason this is here is because we are working in the special GitHub repository associated with this course, where I've made it so that we don't need to have a direct copy of that TensorFlow source code. And so in order to do that, I am importing it externally in the context of Bazel language here. That external depository has an associated workspace name org TensorFlow. I'm probably getting too far in the details already inside of this process, but that is why I've listed those here. Similarly, for the load save model file that we just looked at, I have defined the name to be load save model associated with the CC file, and again the list of TensorFlow dependencies. And I've also said make sure you use the more modern C++ 14 syntax, because I've used fancy things like standard make shared, which require more modern compiler. My default version of GCC, for those wondering, is 5.4.0. And real quickly, at risk of being more detailed than I probably should be in this video, we can look at the workspace file associated with this project. I've said the name of our workspace is tfcourse. Again, this workspace file is at the root level of our TensorFlow repository on GitHub that you have access to. And I just want to show you really briefly that there is a workspace.bazel file I've copied over from TensorFlow Serving's GitHub, and it has a function in it called TensorFlow HTTP archive, and that is how I am able to import TensorFlow without having the copy of the source code. I use their HTTP archive function. It has the name TensorFlow, and then I've copied over the same SHA-256 hashes and the git commit from TensorFlow Serving that they're using. So that's what's happening beneath the scenes, and then you've got more detailed, not as important things like external dependencies of TensorFlow and calling the TF workspace function. Again, feel free to read through it yourself. Bazel is a long journey. For those interested in learning about fun build tools like Bazel. For the purposes of this video, we are more concerned with the API, and we will end it with that. Especially relevant for today's video, which has a lot of details. Now that we've got some experience playing with the C++ API, we can move on to TensorFlow Serving in our next video. TensorFlow Serving is built with the C++ API, and it also includes some handy Python interfaces for making requests to your TensorFlow server.